you can question. So now, before giving to the Professor Anand, I will have a 2 minutes with to have a brief about this entire program, how it has happened, because he
2000 data, whatever the physics we have studied, called classical physics. We had Newton's equations, right? So we are all happy with those equations, and even our space technology was developed on the basis of Newton's laws. But in the year 2000, సడన్గా ఏమైందంటే మ్యాక్స్ ప్లాంక్ అని ఒక సైంటిస్ట్ ఏం చేశాడు, టు ఎక్స్ప్లెయిన్ ది బ్లాక్ బాడీ స్పెక్ట్రమ్ he said, light is not a wave, but light is made up of quantum of energy అని అన్నాడు. Using that concept, he develops quantum theory, and then Einstein comes into the picture. Our own Indian great scientist Satyendranath Bose also comes into the picture there. That is how the quantum physics was developed. కానీ 1924-27 కంతా ఫిజిక్స్ ఒక ఫిలాసఫీగా అయిపోయింది, మీకు తెలీదో లేదో. హైజెన్బర్గ్ అని ఒక సైంటిస్ట్ ఉన్నాడు అప్పుడు. ఆయన ఏం చెప్పాడంటే, నథింగ్ కెన్ బి మెజర్, ఎస్పెషలీ ఎక్కడ ఈ వస్తువు ఎక్కడుంది అంటే మేము ఖచ్చితంగా చెప్పలేము అంటాడు. ఈ వస్తువుకి ఎంత స్పీడు ఆ మొమెంటం ఉంది అంటే దాన్ని ఖచ్చితంగా మేము చెప్పలేము. సో యు ఆర్ అనేబుల్ టు మెజర్ సర్టన్లీ ది పొజిషన్ అండ్ మొమెంటమ్ అని. ఇది ఇట్ వాజ్ ఏ బిగ్ ప్రాబ్లమ్ ఫర్ ది సైంటిస్ట్. ఎందుకంటే మనం ఫిజిక్స్లో ఏం చెప్తాం చెప్పండి, ఫిజిక్స్ ఈజ్ ప్రిసైజ్. ఏం నేర్పిస్తాం మేము? ఫిజిక్స్ ఈజ్ ప్రిసైజ్. ఖచ్చితంగా ఇంత రావాలి, 9.8 రావాలి, జీ అంటే 9.8 రావాలి అని. ఆయన అలా చెప్పలేదు. దెర్ ఆర్ అన్సర్టనిటీస్ బై నేచర్ ఇట్ సెల్ఫ్, నాట్ డ్యూ టు ఎనీ ఇన్స్ట్రుమెంట్. సో అది ఒకటి ల్యాండ్ మార్క్ జడ్జ్మెంట్. నీల్ బోహర్ ఒక క్వాంటమ్ కండిషన్ తెస్తాడు. ఏది? ఇప్పుడు మీరంతా యాటంలో ఎలక్ట్రాన్స్ అరేంజ్ అయ్యే ముందు ఫస్ట్ ఆర్బిట్లో 2 ఉండాలి, సెకండ్ ఆర్బిట్లో 8 ఉండాలి, థర్డ్ ఆర్బిట్ రఫ్గా 18 ఉండాలి అని చెప్పుకుంటూ పోతాడు. ఇంకా ముందు ఏం చెప్తాడు, ఎంత దూరం ఉంటే అంత దానికి కైనెటిక్ ఎనర్జీ డిఫరెంట్ ఉంటుంది. సో హయ్యర్ పైన నుండి మీరు ఇక్కడే ఉన్నారు, అక్కడ నుండి ఇక్కడ రావాలా అనుకోండి, పైన నుండి కిందకి వస్తే మీరు ఆర్ గెయినింగ్ ఎనర్జీ ఆర్ లూజింగ్ ఎనర్జీ. యూ డోంట్ లూజ్ మచ్ ఎనర్జీ, బట్ వైల్ గోయింగ్ అప్ యూ లూజ్ ఎనర్జీ. సో ఇటువంటి ఐడియాసే చెప్తాడు. ఎలాగా క్లాస్లో ఆ అబ్బాయి ఈ బెంచ్లోనే కూర్చోవాలి, 2 బెంచ్ల మధ్య ఎవరైనా కూర్చుంటారా? లేదు. ప్యాసేజ్లో కూర్చుంటారా? లేదు. సో హీ సేస్ ఫర్బిడన్. ఇన్ బిట్వీన్ దీస్ ఆర్బిట్స్ ఎలక్ట్రాన్స్ ఆర్ ఫర్బిడన్. దే కెన్ ఓన్లీ ఆక్యుపై స్పెసిఫిక్ పొజిషన్స్. దట్ ఈస్ వాట్ హీ మీన్స్ బై క్వాంటైజ్డ్ ఆర్బిట్స్ అని చేస్తాడు. ఎలా ప్లాంక్ క్వాంటమ్ ఎనర్జీని తెచ్చాడో, నీల్ బోహర్ గోస్ ఎ స్టెప్ ఫర్దర్ అండ్ సేస్ ఇట్ ఈస్ క్వాంటైజ్డ్ ఆర్బిట్స్ అని చెప్తాడు. ఐన్స్టైన్ మహానుభావుడు, తెలుసు కదా మీకు, ఆయన చెప్పేస్తాడు, ఈజీగా చెప్పేస్తాడు, ఎవ్రీ లైట్ రేడియేషన్ ఈజ్ మేడ్ అప్ ఆఫ్ స్మాల్ ప్యాకెట్స్ ఆఫ్ ఎనర్జీ అండ్ ఈచ్ ఫోటాన్, ఈచ్ ప్యాకెట్ ఈజ్ కాల్డ్ యాజ్ ఎ ఫోటాన్. ఇలాగుండింది. కానీ దెన్ కమ్స్ అనదర్ సైంటిస్ట్, మై నేమ్ ష్రోడింగర్. హీ బ్రింగ్స్ అబౌట్ ఎ లాట్ ఆఫ్ చేంజ్. ఆయన ఫిలాసఫీ తెచ్చేస్తాడు. ఆయన వన్ పార్టికల్ కెన్ ఆక్యుపై డిఫరెంట్ పొజిషన్స్ అట్ ది సేమ్ టైం. ఒప్పుకుంటారా? ఎక్కడుంది అంటే ఇక్కడ ఉంది అని చెప్తాం మేము. ఇక్కడ ఉంది అని రేల్ చూపిస్తే అక్కడ ఉంది అని డెఫినెట్ కదా? లేదా ఆయన చెప్తాడు, ఇట్ కెనాట్ బి డెఫినెట్. ఇట్ కెన్ బి హియర్, ఇట్ కెన్ బి హియర్, ఇట్ కెన్ బి హియర్, ఇట్ కెన్ బి హియర్, ఇట్ కెన్ బి హియర్. దట్ ఈస్ కాల్డ్ సూపర్ పొజిషన్ స్టేట్స్ అని చేస్తాడు. దిస్ వాజ్ వెరీ డిఫికల్ట్ టు డైజెస్ట్ ఫర్ పీపుల్, బట్ స్టిల్ నమ్ముతారు. పెద్ద సైంటిస్టులు చెప్పినప్పుడు నమ్మాలి, అలాగే రీసెర్చ్ చేసుకుంటూ పోవాలి. ఇలా ఉన్నప్పుడు ఇఫ్ ఏ పార్టికల్ కెన్ బి ఇన్ 2 states అన్నప్పుడు దెన్ హీ ఇంట్రడ్యూసెస్ దిస్ క్వాంటమ్ ఎంటాంగిల్మెంట్. ఐన్స్టైన్ చెప్తాడు, కాదయ్యా నువ్వేమంత ఈజీగా చెప్పేస్తావు, ఇట్లయితే 2 particles కెన్ బి ఎంటాంగిల్డ్ అంటే అర్థమైంది. ఇఫ్ 1 particle కెన్ టేక్ డిఫరెంట్ పొజిషన్స్, హీ సేస్ 2 particles at different positions కెన్ ఆల్సో బి టుగెదర్. మీరు ఎక్కడున్నారు, నేను ఇక్కడున్నాను, బట్ అవర్ మైండ్స్ ఆర్ కనెక్టెడ్. అట్లా తెస్తాడు అనమాట ఆయన. సో దట్ ఈస్ కాల్డ్ ఎంటాంగిల్మెంట్. ఎంటాంగిల్డ్ మైండ్స్ అంటారు, ఇప్పుడు ఎంటాంగిల్డ్ సోల్స్ అంటారు, అవును కదా? సో ఇన్ ఫిజిక్స్ వీ సే ఎంటాంగిల్డ్ పార్టికల్స్. ఇది ఐన్స్టైన్ నమ్మడం అనమాట. It went on for about 60, 70 years, people arguing, discussing, doing experiments, either for or against. చేసుకుంటూ ఆఖరికి some 30 years back, 20 or 30 years back, ఒక ఫ్రెంచ్ సైంటిస్ట్ బై నేమ్ ఆస్పెక్ట్ ఒక ఎక్స్పెరిమెంట్ చేస్తాడు. వెరీ రీసెంట్లీ జైలింగర్ అని ఆయన ఒక ఎక్స్పెరిమెంట్ చేస్తాడు. ఈయన ఈ ముగ్గురు కలిసి ఎక్స్పెరిమెంట్స్లో చూపించేస్తారు అనమాట. ఏమి ఎంటాంగిల్మెంట్ ఈజ్ రియల్ అని, ఎంటాంగిల్మెంట్ ఈజ్ రియల్ అని. బేస్డ్ ఆన్ దిస్ ఎంటాంగిల్మెంట్, దట్ ఈస్ సూపర్ పొజిషన్, we go to quantum computers. So physics ends here and then computers will take the position. So my friend will speak about the quantum computers. ఇంకొకటి చెప్తాను సార్, we have very few people who can talk on quantum computers because it's a very recent subject. కాలేజీల్లో కూడా లాస్ట్ ఇయర్ ఇంట్రొడ్యూస్ చేశారు. 2 years back our central government gave nearly 8,000 crore for the next 3 or 4 years to be spent on quantum technologies. Now everybody realized, oh, there is a quantum technology, be in quantum computers. It's a hard subject now. So it is a very recent subject, but I am sure my young friend will make it more and more clear. If you do not understand, don't worry about it. Try to follow because it's a new subject. At the end, you can raise some questions. Okay? Let us listen to Anand.
Thank you, sir, for giving me opportunity to come over here because I am a little bit passionate to share knowledge, whatever I have. So, frankly speaking, I am not an expert in quantum computers. Only thing is, basically, I am a physics background person, heading a computer group in Assam, working in satellite communication. So, all these three synergic, I took interest and started passion learning about that. So last 1 year almost I have made an attempt to, whatever I gained, I try to share with people in the school level to engineering colleges level. So thank you for that. So with that basic introduction, next, yeah. See, Gordon Moore is a founder of Intel Corporation, chips hai na? Okay, so he made a prediction that the number of transistors which can be put it on a chips now will start increasing every 18 months and it will get saturated. Today you have mobiles and you have got SIM so miniaturized that will get saturated. So beyond certain level you cannot bring down the size of the chip, you cannot bring down. So then there is a saturation of Moore's law, and then with the growth of electronics and the saturation of Moore's law, where the size of the chips, electronics, semiconductor chips, you can. What are the other ways you can increase the computing power? Because there is a limitation in memory also. In classical computers, whatever you see, whether it is a laptop or a desktop, each time you have to scale up. Okay, so there are limitations. So quantum computing became one of the ways. Next, see now, as on now, we have device, very small devices. Very small chips, a lot of information has been put, and now there is a threshold limit through which you can go on reducing the size. And typically, when you go to the level of 10 to the power of minus 9, means 1 over 10 into 10 into 9 times, that much centimeter level, where physical properties will suddenly get changed. The laws of classical physics are known, whatever sir said, are no longer valid. You get a wonderful new generation of properties which you don't expect. So that is what you are seeing a threshold as nanotechnology or nanoscience, 10 to the power of minus 9 centimeter level. Okay, next, quantum, please see, go, previous, yeah. See, quantum computing is one of that. Quantum computing provides a theoretical framework for computing using, there is a branch of physics called quantum mechanics. Using those fundamental principles, we try to explain that. Now, before I go to the next slide, you have to change your perception slightly. Normally, when you look at a computer, what comes to your mind is a laptop, a screen, a keyboard, a mouse, a processor, or other things. These are physical hardware. If it is a desktop, you have a TFT monitor and all other things, other extra drives. Okay. This is a physical hardware, normally what you think about a computer. And now you have to change your mindset change your perception that instead of a physical hardware, what is being there, a laptop, you think that you are going inside an atom. You are using fundamental particles like electrons or atoms, or what Sir says about photons. Those fundamental quantities we are going to use, their physical properties we use to store, retrieve, transfer and revolutionize information. You got my point? We use the properties of these fundamental particles, electrons, photons, atoms. You use to store, retrieve, transfer information. Instead of a physical hardware, we go to that level. I will come back. There is a hardware required for quantum computers also. But we use these kind of fundamental particles and their behavior. Okay? That is quantum computing. Next. As quantum physics, quantum physics is actually study of particles of atomic and subatomic particles. Suppose if you are inside the nucleus, you say it is nuclear physics. Outside the nucleus, it is atomic physics. Okay. So there are, I had already said Planck's equation. So this is what you are seeing, electrons revolving around the nucleus with speed equivalent to almost velocity of light, 3 kilometers per, almost near to that. Next. See, now, before we go, I want to give you some live examples where quantum physics major place few technologies in a common manner you are seeing. In electronics and semiconductors, the principles of quantum mechanics, whatever semiconductor chips you are using in all the electronic industry is because of quantum physics, including transistors and other things. And you have got lasers. Laser treatment you are using for many other purposes, whether it is a cancer treatment for any other shows, no? So laser is also based on your quantum physics. Next. And LEDs, whatever, light emitting diode, the solar cells, their functionality is also based on your quantum physics. Again, you have CT scan and MRI scan, the imaging, no? Again, that is based on your quantum physics. Then atomic clocks. Now you are using GPS, okay? So GPS, whatever your timing and position accuracy you are getting, that is based on a payload in the navigation satellite called atomic clocks. Again, quantum physics comes into picture. Okay, next. Nanotechnology, already I told you, okay, that is available. And superconductivity is actually normally when the electric current flows through your wires, no, there is a loss of energy, one place to other. But when you bring down the temperature to certain level, the current will flow from one place to other without any loss of current. So that phenomenon is called superconductivity. So superconductivity also have quantum bending. So principles of quantum physics are directly apparent. There are so many activities and technologies which you are enjoying in your daily life. Okay, next. Yeah, see normally quantum mechanics is already see when you try to formulate a theory, you should mathematically prove it. Unless you prove, no, there is no meaning. So normally the quantum mechanics is a mathematical framework for the development of physical theories. Whatever physical theories which you are proposing, no, you have to prove it. So there is a qualitative, suppose if you are not able to prove it mathematically, it is only qualitative. Then in quantitative you have to prove it mathematically. So quantum mechanics actually there are 3 fundamental laws. Already Sir has told one size, Heisenberg consultative principle he has already told, like different orbits. Second is Pauli's exclusion principle, no 2 electrons have the same spin on the same orbit. And third one is the Schrodinger wave equation, like how the wave propagates over time. Okay, time dependency has already explained. So these 3 laws you just remember. Okay, next. Yeah, now let us come to the classical computers. When I switch on, the light switch I switch on, light become on. Unless you switch on, when the switch is off, no current is flowing. Means that there is no information. That is 0. When I switch on, light becomes on. There is current flow. That is as 1. So in classical computers, whatever any other systems, the information is represented as a string of electrical pulses as zeros and ones, like a switch. When you switch on, there is an information 1. When you switch it off, there is no information, it is 0. And similarly, for example, it is something like whatever light switch I told, or any of switching on the computers. It's as good as that. In quantum computing is a new kind of computing which takes the laws of quantum mechanics. And second thing, till you switch on the light, here it will be dark. You know that when you switch on, the light will become on, means your results, you know what you are going, once you do the operation of switching on, the switch on the switch, no, current will glow, so the bulb will glow. You know that it's going to bulb will glow, means that you are sure of knowing the result by doing that particular operation. Means that we also call it as deterministic. Means that by doing some operation, well before I know what is the result I am going to get. Now I take a coin, I toss a coin, till it falls down, I do not know you are going to head or tail. So there is a 50% chance that head is going to come, there is a 50% chance that tail is going to come. So there is a probability of getting head is 50%, the probability of getting tail is also 50%. So when you go for quantum computing, the results are probabilistic till the results are measured. Whereas in classical computing, you are well known that when I do this operation, I am going to get this result. But whereas in the case of quantum computing, till I make a measurement, I cannot surely predict that this is the result, this is the result you are going to get. I can only say in terms of percentage, 50% only head can come, 50% probability only tail can come. Okay, that is one term. Next. So this is what I was telling. Classical computers, whatever you type it on the laptop, no, they are all called ASCII characters. They are translated to string of electrical pulse representing as 0 and 1. When no information is there, it is 0. When something information is there, it is 1. The string of electrical pulses, whatever you are typing. Next. See now, that's all already explained. See typically, see now, I gave an example that here it is, we call it as bits. A small piece of information that is 0 or 1, we call it as bits. Here we call it as quantum bits. Now, in the first slide, I have shown one figure. The electrons are revolving round the orbit in different, as Sir said, different energy orbits with the speed equivalent to velocity of light. At any instant of time, if I want to find out precisely the position of an electron, it is really challenging. Because you have to give a probe, you have to make a measurement, you have to sense it also. It's not easy. So when I try to take a measurement, you feel that electron is revolving around different orbits simultaneously because no such probe is available to precisely tell this is the position of the electron. So that I call it as superposition. Once I make a measurement, electron will get collapsed either in the lowest energy orbit or next higher energy orbit, whichever is there. Depending on which energy level it is there, it collapses to the next energy level, losing the energy. Till you make a measurement, it can be there in any number of orbits. Now, for example, so qubits can be an atom. Photon is the smallest quantity of energy, that is the quanta, that is given by one formula, or any other electric circuits. Next. Yeah, this is what I was telling. I gave an example of the difference between classical computing and quantum computing. My results are probability. And second thing I want to tell you, now, you three people are there. I gave an example, I guess. You people are looking at me now. Now, assume that you are 3 electrons. You are looking at me. If I make a measurement, you are looking at me. This is one measurement, is one quantum state. Now I ask this teacher will not turn. I ask you to change your direction. Now you 2 people are looking at me. The other fellow has turned like this. This is another state. I ask you to turn you also. I don't know whether you can turn. Yeah. So now you are looking at it. So this is not this. So with 3 people, I have got 2 cubed, 8 combinations. There are 8 combinations with which these 3 electrons can be there in different orbits simultaneously. But then you can come back, sir. Now, these are called quantum states. With 3 electrons, I gave 8 combinations. 3 I have demonstrated. Like this I can demonstrate there are 8 combinations with 3. 8 combinations. Now, till I make a measurement, these 3 electrons can be there in 8 different combinations. Suppose if I take 4th one, it becomes... If the number of electrons or the qubits increases, the computing power increases exponentially. 2 to the power of n. Whereas in classical computers, with 5 electrons say, you have got only one combination. But here you have got 2 to the power of 5, 32 combinations. So computing power is increasing by 32 times. Once I make a measurement, it collapses to one of these combinations. When I try to change the state, no, all the 32 combinations will get changed simultaneously. That is the beauty of quantum computing. Okay, next. Yeah, see, this is the way I was telling the primary switch when you switch on light, when light is blown, it is 1, when light is not. So this is the way, the string of electrical pulses. Next. Yeah, already sir has told that the photons have got both wave nature and depending on the type of this, so it can be a wave or this. So from examples, for example, matter as particles, like so photoelectric effect, you have an example for a particle nature. Wave nature, there is for example, ripples in a pond, light as a wave. So there are so many examples there. Okay, next. They are dual nature. So there are experiments where light behaves as a wave in experiments like diffraction and interference, and light behaves in photoelectric effect. So electrons also behaves as particles, like collisions in waves in diffraction. Next. Yeah, this is what I was trying to say. So particle nature and the wave nature of light. Next. Yeah. So quantum mechanics, already I told you, is a mathematical framework for proving physical theories. And then superposition, I already told you that 3 electrons, I gave the example of this. So till you make a measurement, all the electrons can be there in all the orbits simultaneously, that Hubble combination. Once I make a measurement to find out precisely the position of the electron, you get one of the combinations out of 8. If it is 4, one of the 16 combinations. So your computing power, now assume that electron is like something like a small bar magnet. Electron is like having a small bar magnet. So normally in bar magnet you have a north pole and south pole. Here we call it as a spin. Either it will be looking up like this or it will be looking like this. So what we use, one of the properties is the spin direction to store information. Yeah, anti-clockwise. That is one part. Second one is when like the photons travel in space, no, they take different shapes. We call it as spatial modes. So spatial modes is another property which we use for storing and retrieving information. Third one is called the polarization. Polarization, we use polarization direction also as one of the properties to store and retrieve information and manipulate it. So these are the properties we are using. Now finally, a qubit can be an electron, an atom, or a photon. So now, if you try to look at the physical hardware like laptop, a quantum computer will have a hardware which can generate these quantum systems, means like electrons, photons, or atoms trapped in between the magnetic field. That state transition from one electron orbit to next orbit is controlled by an external source using a microwave source or laser source. You have got a sensor to measure whether it goes from higher energy level, and we make the electrons to interact. So this is the way of looking at a quantum computer, where systems which can generate these fundamental particles and external sources to manipulate its state. There are sensors to look at it, whether it has jumped from lower energy to high energy level, and make the measurements. This is the way we do. Next. So this is what I was telling. Sir has told that chronology, like the innermost orbit is 0, the outermost orbit is 1. Next. Yeah, this is what I was telling. Classical bits and quantum bits. See, classical bits are like spinning of a coin. Instead of one coin, if I toss 2 coins, you got 4 combinations. When I toss 3 coins, you have got 8 possible combinations. Like spinning, like 3 electrons I told you. Okay? Next. Now the qubits, the spin direction I was telling, up or down, no? This is the way I can represent the information. So now, if it is exactly there in the lower energy state, it is 0. It is there in the excited energy state in 1. But unfortunately, this information is very, very delicate. So what we have to store in a memory, like normally you are storing information in computers using a memory or a chip, no? We have to store information related to the spin direction of an electron, Or I told one more word called the spatial modes, which you may not know, but anyway, just hear it. And other one is the polarization, direction. That information we have to store in the memory sufficient long enough that we should be able to make decision. But unfortunately, this, what we call quantum information, the spin direction, all these things will get affected by the noise inside. Noise inside the sense by the thermal noise, because the circuit may generate noise. So if suddenly the electron which is excited to higher, it will make it collapse to the lower level. So if suppose if we have made a measurement, electron is there in the ground state having upspin. Before I make the next measurement, suddenly because of the noise, the electron may get excited to higher level, which we will not come to know. So there is a possibility of an error that we have to detect and correct. So it is very, very delicate. Next. Yeah, this is what I was telling, superposition. So we can have multiple two with two electrons. Next. Yeah, this is what I was telling, spinning of the heads. I gave an example of probability of 50%. Next. Yeah. So now, Siamese twins, whether you have, sir has told about entanglement. Now assume that Siamese twins, you have heard, two heads and one body. Human beings would have seen. So one head, one baby, the other fellow, the other way, it also automatically turns. It is like, so now you two are teachers. You are very good friends. Now as long as you are sitting separately, your behavior normally in terms of physics be represented by what is called the wave function. You don't worry, it is a mathematical formulation which gives information about position and time. Now somehow you are two good friends, you interact. Your behavior is collected. Now once I correlate your behavior, you two people, I cannot treat you as independently. Okay? As long as you are separate, your behaviors are different. I have correlated your behavior. Similarly, I have two electrons one having upspin and downspin, separated by different what is called wave function, a mathematical formulation. I make the electrons to interact. I make their physical properties to get correlated, means the spin direction. So once I correlate these spin directions, I cannot treat these two electrons separate. You should treat it as only one. So when I correlate these properties of two electrons, I do not know this cell is having upspin, this cell is having downspin, I don't know. Once I entangle, means when I correlate the physical property of the spin of these two people, I do not know who is having upspin and downspin till I make a measurement. The beauty is your correlated property remained entangled even if you linearly separate it. Now, suppose if I make a measurement that to find out what is the spin direction of SR1, he is having upspin. The moment I come to know he is having, you will immediately adjust that you should have downspin. That is as per the quantum mechanical rules. Now assume that this cell is there in Earth. I am taking you to Milky Way galaxy. You are linearly separated. Now, what I do not know both of them. I have made a measurement. He was having upspin. You are there in a Milky Way galaxy. You will immediately come to know I should have downspin. You will have downspin. Now, what I do some operation. I will change his spin direction from upspin. I will impinge a photon. I will excite it to next energy level. He upspin to downspin. He will go. Momently you are there in a Milky Way galaxy. You will also change automatically from downspin to upspin. Means that this is an instantaneous effect, a non-local effect. Irrespective of the linear distance, the properties gets correlated. This is not a science fiction, this is reality. This is quantum entanglement. Now I come back. Now, Einstein has told no particle in the universe can travel greater than the velocity of light. Here there is a non-local phenomena where two electrons or two people, one fellow is there on Earth, the other fellow is there in a Milky Way galaxy. where their physical properties are correlated. One will change, other automatically change, where there is an information transfer greater than the velocity of light, which violates the theory of relativity. So now, since Einstein he was not able to explain, he called it as a paradox. He thought that okay, it is something like some unknown quantum mechanics is simply it is not correct. We know some hidden things are there, so we are not able to explain. Later, already sir has told Niels Bohr and other there are three people, Elstein, Podolsky, and North and Rosen. They predicted, but what Einstein told was wrong. So means that two quantum systems, electron or atom or any other thing, photons, if their physical properties are correlated, they remain correlated forever, even though they are linearly separated by thousands of light years away. This is the beauty of this. So one is superposition, like it can be there in the orbit simultaneously. The other one is the quantum entanglement. There is one more concept called interference. Next. So this is what I was telling. Sir, one is there in Earth, other one is there in Milky Way galaxy. Their properties will remain correlated. Next. This is what I was telling. So till I make a measurement, I will not know whether he is having up spin or down spin. Once I make a measurement, one fellow is up, the other fellow will adjust automatically. And when you change the one, other also will change instantaneously. This concept is used for implementing practically what is called quantum teleportation, where physically we are not transferring the information, we are only transferring between source A to source B, two places. But for example, from Kuppam to Bangalore, we don't change, it will change, this is called quantum teleportation. Next slide please. This is what I was telling, a light photon can be polarized in two different directions. It's actually called differential direction in the sense that it's the electric vector representation, okay? Fine, next. See, Nobel Prize for the 2022 was awarded to three people, where the allied suspect John Clauser for proving the concept of entanglement. Next. See, application of quantum entanglement is called teleportation, where information can be transferred from very secured information, secret information can be transferred from here to US. Nobody can detect, nobody can intercept. Okay? So physically we are not transferring that, we are transferring only this, whatever I told about the spin direction. This information is transferred between, from, for example, from Bangalore to say Kuppam, so I transfer that information over a classical channel or this information, actual information I don't send. I send only these states which are known to these two people. Okay. The beauty is, normally in any other telephone, you will hear about telephone tapping. Somebody can hack and hear what you are doing. Hacking can be done. That is classical. Here, once you do entangled things, quantum systems, if third person, some third enemy come to know what keys are being transmitted between source, these two people will come to know well in advance that somebody is trying to hack. So we'll say what we call reject that information. So means that nobody in the world can hack without measuring it. Normally in other case, hacking can be done by credit card data, bank data, without your notice, people can hack. But here it is not so. Here it is called US traffic, where it is not possible. So two entangled particles, they will come to know priorly, and okay, this is the other application. Next. Quantum teleportation. So basically quantum teleportation is that using this entanglement concept, we can send information from one place to another place without actually sending it, only we change only the states. The states, whatever there, we can use it for what we call normally when you want to send information in a coded way, we call it as encryption. We can encrypt a message and send. Using this quantum information like spin direction, we can generate a key which is known to by the sender and the receiver, and we can encode the information and send. We call it as quantum cryptography. Very secured information, particularly sensitive information related to defense, we can make use of that. Okay, that is a quantum teleportation is a. So Einstein he called it as called spooky action at a distance. He coined a word called something like some unknown brute force is doing this. Okay, next. So this is what quantum teleportation. For example, from India to USA, I can send information, secured information, without physically transferring it, only by exchanging this quantum information, that whatever the entangled pair of the quantum state, like spin direction or a photon or a spatial mode, using a classical channel like optical fiber or satellite. Physical information is not transferred. So the secure information transfer is that. Next. So this is what I was studying. Next. Yeah, next. Next. Yeah. Quantum, see, this already explained. Next. Next. Yeah. See, normally light waves, no? Photons. When it travels, I can go like this and reach you. I can go like this. I can go like this. So when these different photons travel, no, they interfere with each other in their path. They cross their trajectories. While they are crossing the trajectories, sometimes they aid in information transfer, which we call it as constructive interference. Sometimes while we are crossing, no, we go in opposite direction, we cancel out each other. That is called destructive interference. So interference principles are used for quantum communication. Just remember, this is another concept which we are using. Again, I am giving an example where light photons can travel in different directions to reach the end destination. You are seeing 2 points, no? First point, second point. The photons can travel in different directions. Some places you are getting the signal is you are having a higher wave. Some places you are getting a small wave. Okay, next. Yeah, this is what I was trying. Okay, so sometimes while going, they cross each other. While crossing, it will increase the signal level. In cases they cancel out, that is destructive. So that is being used. That principle is also used. Next. Yeah. See, quantum interference has got so many applications in what are called quantum gates, error correction, interference quantum network. These are applications which you just remember. Next. Yeah. See, normally when you are given a problem, what you do? You make homework. You write the steps. You write the steps. How to solve the problem. So the step-by-step of procedure of writing how to solve a problem is called an algorithm. You can represent the algorithm in different ways. By a pictorial representation, what is called flowcharting. I have written. And you can make decisions also. Suppose if this is there, this way. If this way, you go to a different path. Fine? So this is what is called, so an algorithm is a set of instructions that is designed to complete a particular task. For example, a mathematical problem. I can write different steps. I can represent in terms pictorially. Okay? Next. So classical algorithms, actually systematic methods used to solve problems in conventional computers. See, conventional computers, you can write programs, you can execute the program and solve a problem. So key concepts, the visual representation using diagrams. Okay? And second thing, itself in planning, before writing the code, I can write by diagrams. I can understand the flow. Anywhere I am making a mistake, any step is there. Okay, they can also graphically represent using flowcharting. So now, in the case of classical thing, already I said, I know when I execute the particular program in a computer, I know what is the end result. So it is deterministic. I am able to predict the result. For a given set of inputs, I expect what is the output I am going to get. Whereas in classical computers, whereas in quantum computers, I already told you, like a spinning of a coin or a tossing of a coin. I don't know whether 100% I am going to get the result, 50% I am going to get the result. Next. So similarly, classical algorithm, for example, there are so many. See, for example, what happens? There are such algorithms. You don't worry about that. See, normally, what happens is there are two things. When you run a program or any application in a computer, two things you should worry. One is the time complexity, what we call, means that whether the program which you are running an application, whether it is on a mobile or a computer, how long it takes. The less time it takes, the program is efficient. So time complexity is very, very important. Second one is space complexity. When you run a program, your mobile should not become slow, or your computer should not become slow. Because sometimes when you try to book on a website, server not responding, payment gateway doesn't come because it is compute incentive. So resources which is used is too much. So it should be, time complexity wise it should be low. resource wise, also it should take low resources, low memory, low internet bandwidth. So these are the two important characteristics. One for look for, that is time complexity measures how a run time of a program. Means that when you write an algorithm and translate it into a program and run, how fast it can execute. That is important. Second one is space complexity. The amount of memory required to run the program means that you should take less memory and less time than what program you have written, whatever algorithm you have written is more efficient, or whatever an optimized solution, what we call. Next. See, quantum algorithms actually uses the principles of quantum mechanics, and they use the principles of superposition, entanglement, whatever I have told till now. Okay, so next. See, basically, I just try to give an example. You now, bank ATMs, you are drawing your money now. Your money is safe. Wait. You are right. Now, when you ATMs are installed with some kind of security only, they would have installed, you are using it. Now, ATMs uses an encryption algorithm called DES, with an assumption that factorizing large numbers is impossible. So they have the security of the ATM depends on there is a computational complexity of the assumption they have made. So means that factorizing large numbers will take hundreds of years. So they have put a security algorithm in DES that they have initialized such a big number using normal computers. It will take hundreds of years. Okay, that is the assumption they have made. They have built, so you are using ATMs. Now you have got best supercomputers available in the world. I am talking about quantum computers. I said your computing power increases exponentially. With 3 bits, it is 2 to the power of 3, 8 times. 16 times compared to normal computers. Whether quantum computers are really powerful compared to normal best supercomputers available in the world today. That's a question mark will come into picture. No, my answer is no. If whatever problems you are facing in day-to-day life, fine. For example, you want to discover a new truck. You want to predict the weather precisely, that it is going to rain. It needs very, very fast computing resources, fast computation power, fast algorithms. Now, whatever problems which you are facing in life, you should be able to represent it as a qubit problem, a quantum problem. Now, in the case of ATM, where people assumed that factorizing large number is impossible, you can represent that security, whatever assumption made, as a quantum algorithm called Shor algorithm, where you can crack that code in few minutes. So bank ATM security, which is based on an assumption that the ATM encryption cannot be touched for hundreds of years. So if I put it on a quantum computer, that algorithm, using a quantum Shor algorithm, it can crack in 7 minutes. So now people are coming out, all the companies are coming out what is called quantum resistance algorithm. So in other words, quantum computers are suited for specific problems like finding a COVID-19. No? COVID-19 quantum computer would have there. You would have got the quantum vaccine in no time, because you have got such a large computing power. And simulations of drugs, protein folding or anything, no? Modeling, your MRI imaging, you can compute so fast. Different views of you can compute so fast using quantum algorithms. So that is one application. So second thing you have got Aadhaar database. 140 crore people are there. Okay? So much information is there. Now, when I make an Aadhaar authentication, sometimes server doesn't respond. Because you have to make a query, fetch the data. How fast, how efficiently fetch the data is a searching algorithm. So, Grover is not a foreigner, he is an Indian. His name is Lavakusha Gottala. Lavakusha. Like, he's called Love Grover. He's an Indian who invented this search algorithm. Where an example of, if you represent a quantum algorithm, I can fetch Aadhaar database in so fast. So these are the quantum optimization. So optimization faster solutions like in logistics, for example, you have thousands of routes, no? Logistical problem, financial modeling, financial analysis, quantum computers will become very handy. Okay, next. So Peter Shore, who cracking of ATM, no? He is the person. Next. Yeah. So difference between already I told you. This is what I already explained. Next. See, quantum operations. Normally, what happens in classical computers, no? When I switch on the gates, we use what is called logic gates. Means that there are basic gates are there, are not and not NAND. You know, you are familiar with that, I feel. Okay, OR gate is actually, as long as the inputs, the information is flowing in both only, if any one of them you get the output. For AND gate, in both the input should be there. And on OR gate, you get the opposite. Okay, like that, the combination. So that is the logic gates which you apply in your electronic circuits. Similarly, in the case of quantum circuit, this one, what we are trying to change? We are trying to change the spin direction electron by exciting an electron from lower energy level to next energy level. Lower energy level you are putting it as 0, excited level you are putting as 1. Okay, so now what we are doing, in order to do that, like conventional logic gates, we have got what are called quantum gates. Similar to that, you don't worry. So basically these quantum gates are all mathematical operations where we write computer programs. To understand that you need mathematics. However, you can write computer programs and change this, okay? That much you know is enough. Quantum operation is basically a mathematical operation to change the state of this electron from higher energy to low energy level through a computer program. Next. Okay, next. Yeah, this already I told you. Next. Yeah, this already I gave an example. This is what we call it as a different symbolic. You have seen that. Next. Okay. Now, in classical computers already I showed you zeros and ones. Whereas quantum computers we have used qubits. We use qubits can lower energy state is 0, high energy state is 1, and multiple qubits can work together. Entanglement superposition I explained. Whether compact computer, I gave an example of AES algorithm bank ATM, just now I told. Next. Yeah. So now, what is the energy required? In classical computers, we have got silicon chips. They consume a lot of power. Okay? Whereas, in the quantum computers, the energy consumption is very, very less. Now, probably, you might have got an idea where what the shape of a quantum computer could be. So now, a quantum hardware is one where the hardware should be able to generate a set of electrons. A group of, you have a like SIM, no? You have a quantum chip which is inserted inside the hardware. Depending on how many, the chip capability, like for example, 105 qubits means it is able to generate 105 electrons simultaneously, which can be controlled, manipulated using an external laser source or a microwave source. And this can be controlled when you bring down the temperature to almost sub-zero level. So what we call it as cryogenic temperature. There are hardware what is called the dilution refrigerator. It's a very complex hardware. The investment wise is millions of dollars. So quantum, in the end I will show one picture of the quantum, how a real quantum computer looks like. So there is energy requirement. So as such, when you try to compare the classical quantum computers, current quantum computers, they occupy 25 to 100 kilowatt. A modern supercomputer, they access millions of watt because of the CMOS chips which are used, silicon chips. Next. Yeah. So why quantum computer? I gave an example of that. One is quantum computers can consider many possibilities of making them faster than certain problem. I gave an example. Like 3 electrons, 8 possibilities are there. Once I make a measurement, you get one of them. But 8 combinations will get changed. So the number of qubits, your computing power will increase to the power of n. To that many number of times. Second one is complex simulation. Like when you want to model the molecules, molecules have different complex structures, new drugs, or weather forecasting, okay, or interaction, which is not possible it will take hundreds of years. Whereas quantum computers can solve modeling, weather forecasting, simulation, new drugs, all these things can be done very fast in quantum cryptography. Because I already told you, secured information transfer from one place to another, we can encode it as an entangled pair. Physical information transfer need not be done. Only this quantum information can send from there. So secured information, particularly military secrets, we can using entanglement, we can do that using quantum entanglement and decodation. Secured information transfer can be done, and energy savings. Next. Yeah. So now quantum computing has got a lot of applications in this. One is the medical imaging reconstruction, for example, MRI, PET, CT. No, you can get faster, more result-oriented imaging using quantum algorithms. Okay, that is one application. You have got remote sensing and satellite data. Satellite data, you can track a particular area, like whatever normally we use imaging for operations. No, they are remote sensing data. So reconstruction of images for better clarity, better interpretation, we can do it faster using quantum computers. Next. So this is one example, medical image reconstruction. I have given simple CT scan, iterating with patches, no? So here sample CT image, COVID-19 diagnosed. When you run on a quantum computer, you are able to diagnose so fast. Okay? Next. So you have got image reconstruction and computer vision. Computer vision is basically your traffic signaling. Depending on you have got AI-enabled cameras. Depending on the traffic density, they automatically channel out. Okay, it takes decisions. It reroutes. So that is computer vision. You have got image encryption and security. Your quantum imaging is also done. Okay, what is called ghost imaging. Next. So you got optical characterization. You have got lot of over and above artificial intelligence. You have quantum. So it has got a severe implication on artificial intelligence, machine learning and deep learning. So it will still enhances your optimization or the efficiency. And you have got cyber security, means that the secured information transfer so that hackers can be avoided. And your climate science modeling and predicting the climate more accurately, you got an application. Next. And what are all the challenges? The biggest problem I told you, this information, that whatever three kinds of information I told now, the spin direction, the polarization state, the phase or the spatial modes, this is the information you have to store it in a memory. You have to store that information in a memory sufficiently long enough so that you can make decisions. If in between, before making decisions, if this information gets corrupted, there is no point in having that. So maintaining, we call it as coherence, because the electron which gets excited to the higher energy may collapse to the lower energy state so far before I make a next measurement. So that is one challenge. Second one is error correction. Suppose if the electron which is excited to the higher, before making a measure, it is there in having downspin. Before make the next measurement, suddenly it drifts to the ground, higher energy state, lower energy state. You should be able to detect it first. Then you should correct also. So that is another challenge. Third one is the size and the cost. Quantum computer design is quite complex and investment. So most of the top companies like IBM, Google, Microsoft, Amazon Web Services, Rigetti, IonQ, all of them, they have investments of millions of dollars. They have kept this quantum compute hardware in a very, very secure way. They are giving access to the public for the researchers over cloud, giving the URL, what we call on the website, based on the registration. Next. Where are we now? Quantum computers today are small, experimental, but they have been used for solve specific problems. And all the companies are taking a lead in quantum computing research. Next. Yeah, this is a typical example how a quantum computer looks like this. So that whatever you are seeing outside is called dilution refrigerators, where you have to maintain the temperature of the quantum chip 2 to 3 milli-degree Kelvin. So low temperature I have to go. They are gold-plated strings. So a quantum chip actually, when I insert, it generates so many number of quantum bits. Quantum bits, so many, depending on what kind of type of you are using, that many bits. Now that bits, that state is manipulated using an external source, using a laser source or a microwave source. You need a sensor to measure whether the spin has changed, polarization state has changed, spatial mode has changed. The problem here is, normally in the conventional computers, once you run a program, you are expected to get the right result once. Here it is probabilistic, means that I do not know I am sure of getting the right result in the first execution, you have to execute a quantum algorithm or a quantum program many number of times to get consistent results. We call it as sampling. We have to run many number of times so that you get consistent results so that you can make decisions. That is another important. So this is a typical IBM quantum computer. Next. So what is the roadmap? See, next to 20 years, the quantum computers are going to solve, most likely to solve many of your real world problems what we see today. Now, as on today, the investment is too heavy, but it is going to revolutionize many areas. And now there is a, for example, as a teachers, if a student gets 100 marks, his first time. Now, when I have developed a quantum chip, I want to say that my quantum chip is capable of solving a problem which a best available supercomputer in the world cannot solve even 1,000 years. A best available supercomputer in the world may take 1,000 years to solve that particular problem. Using a quantum computer, it may not solve also, but when I am using a quantum chip, I can solve that particular problem in few minutes. So now, a company will declare that they have reached a stage of what is called quantum supremacy, where chip is capable of solving a real world problem which best available supercomputers in the world will take thousands or even trillions of years. That stage is called supremacy. Now, normally, instead of going quantum supremacy, let's go for another item. Now you have got 100 marks. Students have got 100 marks. Some person has got 99%. Still 1% is missing. You have to make some effort to get 100. There is 1% gap. Now, in terms of quantum computer, there is another terminology, what is called quantum advantage. First you get 99, then you target for 100. Okay. So quantum advantage is first you try, when I say 99, means that the company will say, I am able to solve a problem better than the best available supercomputer in the world. That is quantum advantage. When I say quantum supremacy, it is an ideal case. I can solve that particular problem where the normal supercomputer will take 1,000 years, I can solve in few minutes. That is quantum supremacy. Okay? So now, quantum computers power grow exponentially, just add in few more qubits, can exponential computing power, like unlimited workers that can work together, not a single person, like a teamwork. Instead of one person, when you have a team as a cohesive work, you have a problem solving capability in quantum computer. Next. So in conclusion, quantum computing is an exciting field. It combines the strange properties of quantum mechanics. It is still in development. It holds a key in solving some of the world's toughest problems. With this, I have made an attempt to give you a quantum computing where not too much, lot of mathematics is there. Some things you may not be able to understand. I have made an attempt to bring it to your level. And we will see a video first. Then if there is any questions, what I spoke now, you have got a very nice video which will give you more information.